Okay, so we are learning about circular motion, uniform circular motion, where the speed is always constant. The speed of the object that is turning around the center is always constant, but keeps changing direction. Okay, so uniform circular motion. And this is going to be very useful to study now gravitational force, and the origins of gravitational force. And what is the idea? So let's try to give some logic to the thoughts. No, imagine Newton. So it goes almost as a legend that Newton was sitting under a tree and an apple fell on his head, and with that he got his great idea about the universal gravitational law. But what is the idea? Suppose you drop an object close to the surface of Earth. Well, the object falls. If you go higher, if you go to the top of a tree and you drop it again, it falls. And so the reasoning was, okay, so now I go to the top of a mountain, it will drop. So if you go on going further and further, you will eventually think that, well, that must be the force that keeps the moon in its orbit. There must be a force attracting the moon, and that's why it keeps rotating around Earth. And then you can say, well, okay, but if there is a force attracting the moon, why it doesn't fall? Now, why doesn't it collapse on Earth? Well, because it has a velocity. No? So it has a velocity, and so all that the force of attraction can do is change its direction. So here in the center we have Earth, okay, and here we have the moon. The moon is attracted by Earth. There is a force attracting the moon, and it's the same force that attracts all the objects that we drop and fall. Okay, so it's the same force as the gravitational force, and you ask why does the moon does not collapse on Earth? Because it has a velocity. It has a velocity, it keeps rotating. All that this force, this gravitational force, can do is change the direction of the velocity. So the moon is at the right height, and it has the right velocity, so that all that the gravitational force does is to keep it to keep the moon along the circular motion, okay, with the constant speed, but changing the direction very often. Now, so this is the idea of the gravitational force. Earth attracting all the objects nearby, but it's a action and reaction. Earth attracts the moon and attracts any other object, while the object reacts and also attracts the Earth. Okay? So this is the idea of the gravitational force. And one more important thing. The moon keeps rotating around Earth. We see the objects falling on the surface. But if we keep going further and further and further, well, eventually this force must get weaker and weaker, because we don't have objects rotating around Earth very, very far from it. So this must be a force that decreases with distance. Another important reason. So this first one is the gravitational force must decrease, must be a ratio of some distance. And we'll see that it decreases at the square of the distance between the two objects. Another important thing is, okay, so if any two objects attract themselves, it's a gravitational force, how come objects on Earth don't collapse against each other? No? How come I don't collapse towards the table and the table doesn't collapse towards a chair and so on? Well, also, this force must depend on the masses of the objects. The bigger they are, the stronger these forces are. So if I take Earth, mass 1, and the moon, mass 2, well, they are very large. So this force is very strong. But if these objects are very small, this force will be not so significant. So this is the idea of the gravitational force. Let's see now what is exactly the value of this force. Important comments. This force is always attractive. It attracts any two objects, attract each other by this gravitational force. They never repel, like electrons repel each other or protons repel each other. The electric force, there is attraction and repulsion. in the gravitational force is always attractive. And so this is the force that keeps not only the moon turning around Earth, but also Earth turning around the sun and all of the other planets rotating around the sun, and also keeps the sun and other stars moving around the center of the galaxies and so on. So there is a lot of motion in the universe. And astronomical objects have very big masses. So this force is really important when we come to discuss the universe. Okay, so this is the force. Now, this was our first attempt, but here you have the exact equation for the force. Now, so as we said, it depends on the two masses. It's inversely proportional to the distance, the square of the distance. And now we should say, distance of what? We said the distance between the two objects, but let's be more precise. Is the distance between the center of the two objects. Okay, so the center of Earth and the center of the moon. So this R that we are talking about is the distance between the center of the two objects. Now, Earth itself has a radius, the moon itself has a radius, but we take into account the whole thing from the center to the other center. Okay, and what else? Now you see a new symbol appear in our equation, which is this G. This G is a constant. No? This is the value of this constant. It's tiny, tiny. And this now tells us why that force becomes so small when we have small masses. Now this constant is so small that the force between small masses will be almost negligible, although it exists. And careful with the units, newtons, because if we are using international system, now the force is in newtons, distance is in meters, so meter square, and mass is in kilograms, so kilogram square. Okay, so now that we've seen the expression for this force, we can try to solve this little problem. And what we have there is two people sitting at a bench. Now, so let's see what is the force between these two people. So we have their masses. One person is 50 kilograms, the other one is 75 kilograms. We have the distance between the center of one and the center of the other is just 0.5 meters, so they are very close. But the masses is very small. Remember, the G here is very small. So if you put these numbers into the equation, the big G, mass of one person, mass of the other person, distance between the center of one person and the other, you will find a tiny force, 10 to minus 6. So it's a force that doesn't have much of an effect. The friction that we have by sitting on this bench is much bigger. Now can easily hold these two people in place so they don't collapse onto each other, even though there is an attractive force between them. Alright, so let's continue. This is an experiment to measure the value of G. It's a very cute experiment. It has to be very precise, but the idea is very simple. Here we have a rod. Forget about this part of the drawing, okay? So let's focus just on this. We have a rod with two balls, and here we have a cord, a fiber, and attached to it we have this mirror, okay? And we have light that reaches this mirror, is reflected and reaches this scale, okay? Now, this is static, but now I bring an object very close to this ball here, okay? Far from them, but very close to this one. And since there is gravitational force, they will be attractive. And so they will attract each other, and this rod will move a tiny bit. This mirror will move a tiny bit. And so the light will now be reflected, but will reach a different point in that scale. And from that, we'll be able to measure the value of G. All right, let's come back to our gravitational force. So this is the expression for the gravitational force, and now what we are writing is, we are writing the gravitational force between an object that we are going to have here on top of the surface of Earth. And so this object has mass m, and I'm going to write here the force between this object, so this object of mass m, and Earth. Okay, and here I'm putting the distance between the center of the object and the center of Earth. Okay? Okay, so this is the force that I'm saying will attract this object. If I drop it, this force will attract it back to the surface of Earth. But before we were talking about another force acting on this object, which was its weight. We said that because of the weight, if I let this object go, it falls. And what is the connection now between the gravitational force and what we were calling before weight? Well, it's exactly the same thing. Okay, the gravitational force and the weight is the same thing. So I can write that mg, that we were using before, is this gravitational force. Okay. And from this, what can we conclude? Well, this is the mass of the object, appears on both equations. Now, what we were saying before, that g, that constant that we were often saying is 9.8 meters per second square, well, now you see that that little g is equal to the big G, to the mass of Earth, and the distance between the center of the object and the center of Earth. So what we are calling little g is big G, mass of Earth, and the distance between the center of Earth and the object. Now, when the object is very close to the surface of Earth, then the distance between the center of Earth and the center of the object is very close to being just the radius of Earth. Okay, so this gives us 9.8 meters per second square. So now you understand where that number was coming from. And you also understand more, because you can see from this equation that if the center of Earth and the center of the object increases, which means if this object goes further and further and further from the center of Earth, this distance here will become bigger and bigger. So that means that G changes. Okay, so G changes. G depends on this distance. Okay, so if we go far away from the center of Earth, G becomes smaller. And this is what this exercise is about. So far we were using just a constant value of G. It was always G equals to 9.8 meters per second square, because we are doing experiments very close to the surface of Earth. But if you start going, so we were very close here to the surface of Earth. But if you start going higher and higher in a mountain, for example the Everest, you will see that this G becomes a little smaller. And this is the purpose of this exercise here. Okay, what we want to compute here is what is the value of G at the top of the Mount Everest. Okay, so to compute that, I write my big G, which is a number that never changes. This is the universal constant and will be given for you in an exam. Okay, then we have the mass of Earth. Okay, and this is also known and it's also given to you. And then we have this distance from the center of Earth to the center of our object. Now, so here we are going to include the whole radius of Earth, which will be given for you too if you need to solve the problem. So this is the one, 6,380 kilometers, plus this height of the Everest. So if you put this 6,380 kilometers, which is the radius of Earth, plus the 8.9 kilometers, which is the height of the Everest, change the units, you will see that then at the top of the Everest, the G is approximately 9.77 meters per second square. So it's smaller than the 9.8 that we've been using so far. All right, some other important comments here. Where is the mass of Earth coming from? Of course, this will be given to you in problems, you don't need to worry. But it's just coming from this expression, right? So I can isolate the mass of Earth and write it in terms of G, R, which is the radius of Earth, and big G. And this is how the mass of Earth was computed. Now, G, we know from the experiment since Galileo, that was approximately 9.8. The radius of Earth is also an old constant, very well known by the Greeks. I'm not going to tell you about this, but if you want to learn more, look for this name, Eratosthenes, who is a Greek who computed the radius of Earth. And all that you have to do to find out this radius is to play a little bit with geometry. You pick two different cities, that's what he did, two different cities from where the distance of which you know, and by playing with studying the shades that the sun makes on the objects on these two cities, you will be able to get this angle here. Now, with this angle and with this distance, and also by knowing that the circumference is 2 pi r, and by knowing that going around the whole circumference is 360 degrees, you play with proportion, with ratios, and you get the ratio of Earth. Okay, so all this to come back to this equation. How is the mass of Earth computed? Well, from that experiment that gave us G, big G, from 9.8 meters per second square obtained with Galileo's experiments, and by the ratio of Earth, which is something that was already known by the Greeks. And then you get to the mass of Earth. All right, so let's move on. Now what we are going to do is, we are going to try to solve a problem. Okay, problem involving Earth and the satellite. So what is the idea? You know that we have many satellites in orbit around Earth, and it's very important to know where you want to keep them, to send them with the right speed. So once they reach the altitude where you want to keep them, they just stay there and keep rotating. Now, if you send them with a small speed, they may just collapse back to Earth. Or if they send them with a big speed, you may eventually lose this satellite. So you have to do this calculation very well. Okay, now what we are going to do is this problem here, and the idea is we want to have a geosynchronous satellite. What does that mean? Geo comes from Earth, and synchronous means synchronized, in synchrony with Earth. So the idea is the following. Suppose this is planet Earth, okay, and this is the satellite. So you know that the planet Earth moves around itself, and that's how we get days and nights, all right? Okay, so here is Earth, and this is my satellite. If it's in synchrony with Earth, that means as Earth moves, this satellite will be always together. So it will be always on top of the same city. That's a geosynchronous satellite. And this is important for TV, for radios, and so on. Okay? So this word here is very important, because by reading this word, we know what is the period of this satellite, right? The period is the same period of Earth. So this is very important information that we are getting just with one word. So the period of this satellite is 24 hours. Now it's 1 day. And careful, because you will have to play with units here and go to seconds. All right, now what is the question? There are two questions. First, they want to know the height above Earth and the speed that this satellite must have so that it doesn't collapse back to Earth and does not escape. Okay, the right speed for that specific height. Okay, so what do we want to do? First, let's think a little bit about this question, the height above Earth. The height above Earth means what? We know that this is the Earth, right? This is my satellite. What we care about is the distance between the center of Earth and the center of the object. This will be the r that will appear in our equations. But what is it that they really want us to give? The height above Earth. So they want this h here. Okay, so be very careful, because when you solve the equations, what you will get is this r, this big R from center to center, which is the radius of Earth here, right? So this is the radius of Earth, plus this height. And what we want is this height. You may ask, well, but don't you have to take into account also the radius of the object? Yeah, when they do the calculation, they take all this into account. It's just that it's so small that it's just included in this h. Okay, so this is what we are going to need to give as an answer to this problem. Okay, so how are we going to solve this problem? Well, we are going to use again Newton's second law. The sum of all the forces is equal to ma. So what are the forces here? We are studying the satellite. So what is the force that this satellite is feeling? Well, gravitational force. So this, and this is the only one. So this is the net force, which is big G mass of the satellite, mass of Earth, divided by the distance between the center of Earth and the center of the object, and this is equal to what? ma. And what is ma? The mass of the satellite, a, right? Which a is that? Well, it's the centripetal acceleration. Now we have this circular motion, this uniform circular motion, so it's the centripetal acceleration. Let me write this a little further, but before we continue, let's just see that we can simplify. No? The mass of the satellite appears here and here, so let's get rid of it. Alright, so now we have g, mass of Earth, we have the distance, we have centripetal acceleration, which is v squared, the speed of the satellite, divided by r. Okay, so things are looking good because g and the mass of Earth will be given to us. I see r here, so we can obtain it. Now I cancel the squared with one of them. But do I have v? No, I don't have v. But we can obtain, we can use an equation for v, right? What we said before, when we have this circular motion, v is 2 pi r divided by the period. Okay, so let's put this back into our equation. Let me go up. Oh, we still have some space. So we have g, mass of Earth, a little r, and now I'm going to put this equation here. So v squared is 4 pi square I square period square. All right? Okay, so now you can use this equation to obtain r. Careful, because how is this equation going to look like? I'm going to put it now at the top there. You will have g, mass of Earth, dt squared, 4 pi squared, and r goes there. So you will have the answer of this problem will be for r cubed. So then you have to do the cubic root to obtain r. Okay, but remember, what you will get is r, which is approximately 42,300 kilometers. But this is not the answer of your problem. Remember that we want h. So you will use this value equals to the radius of Earth, which is given to you, plus h. And then you will obtain h. Okay? Okay, and then comes the next question is, what is the satellite speed? Well, once we got all that, this is going to be easy. Just go back either to the equation for v, 2 pi r divided by the period. Now we have r, so you can get v, or you go back to this equation and get v from there, right? Okay, so let's continue now. Let's come back to that story of the elevator. The elevator, remember we said that when we are inside the elevator, not moving, and if we have this person on top of inside this elevator and on top of a scale, so if we are at rest, or if we are moving up or down with constant speed, then we know that the scale will be given to this person her or his weight. And we can obtain that again by using Newton's law. This is the weight of the person. Because of the contact with the scale, we have Fn. Choose a frame, for example, positive is up. And then from there we obtain, if we at rest, so if v is constant, then we get that Fn minus mg is equal to ma. But if we are at rest or v constant, ma is 0. So then we get that Fn is equal to mg. So the scale will be giving exactly the person's weight. Okay, but now, if instead of being at constant velocity or at rest, this elevator starts accelerating up, for example. Well, if it's accelerating up, we know that this is not going to be 0 anymore. We will have to include ma positive because of my choice of frame. And then from here we know that if we're moving up, accelerating up, then Fn will be larger than mg. Right? Finally, if we assume that this elevator is going down, accelerating down. Okay. So if it's accelerating down, then here we'll have to put minus ma, and then we see that what the scale will be giving us will be Fn equals to mg minus ma. So this person will look lighter. The scale will be giving her not her real weight, something a little less. And then comes now another point to consider. Suppose that the cords that were holding this elevator actually are broken. So the elevator, the person, and everything that is inside this elevator are now falling, but free fall. So this A is just G. So if this A is just G, you see that the person will have this sense, this weightless sense. She will look at the scale and see 0. She will feel as if she was not, as if she had no weight. And everything inside this elevator would be falling together with her. So she would be having this sense as if everything was floating in the sky. There is a very nice movie at YouTube. There are several movies at YouTube about that, how astronauts get prepared before they go out in space where there is no gravity. So how do you get prepared for this sensation of weightlessness? So one plane that even people who are not astronauts can go and have fun, and this is the 0G plane. So look for that in YouTube, for example, and you have some interesting movies about the normal people in this situation of no weight, this sense of no weight. Okay, all right. So the last thing that I want to talk about is Kepler's law. Kepler, who came before Newton, was Galileo's contemporary, came up with 3 laws. So before the gravitational law created by Newton, Kepler came with 3 beautiful laws, and this he obtained just by observation. He wrote notebooks with notes about the positions and the times of the astronomical objects in the sky. And he came with these 3 laws. One was that all the objects, all the planets were orbiting around the sun. In a time where people were still convinced that the Earth was the center of the universe, he was saying that the planets were moving around the sun, so there was nothing that special about Earth anymore. And not only that, these planets were moving around the sun, but not in a perfect circle. These orbits were actually ellipses. Okay? And the sun was in one of these foci, okay? in one focus. The other thing that he noticed by his observations was that the time that it takes, so this is Earth, and let's assume that this is a planet rotating, moving around the sun. So the time that it takes for this object to sweep, you see this shaded area here, is to sweep this area, is the same that it takes to sweep this other area. Now, if this shaded area is equal to this shaded area, if the number associated with this area is the same, so the time that it takes for this planet to go from 1 to 2 is the same time that it takes for it to go to 3 to 4. Okay, so this time is the same, which means that to go from 1 to 2, since this arc is a little bigger, right? So it goes a little faster. So the speed is not exactly constant because we have this ellipse. And finally, the other thing was that he notes that pick 2 planets. Okay, so here is the sun in one of the foci. So here is one planet, so I'll call it planet 1. And here we have another planet, a little further, planet 2. So he notes that the period for one planet, the ratio between the period of one planet and the other, squared, was equal to the ratio between this distance, S1, so the shortest distance between planet 1 and the sun, is this S1, and S2 is the distance, the shortest distance between planet 2 and the Sun. So this ratio of S1, S2 cubed. Okay, so he found this equality, that the ratio of two planet squares was equal to the ratio of the closest distance of these two planets to the Sun cubed. Okay, now we are going to derive something similar to this expression, but not playing with ellipse, so not playing with S1 and S2, we are going to play with circles. These ellipses, they are not too elongated, okay, so they are very close to real circles, and so let's just simplify our lives and try to obtain this expression, but now playing with the radius. Okay, so this is the Sun. Here we have this planet 1. Okay, the Sun is much, much bigger. Okay, nothing is in scale here. So this is planet 1. And around here we have planet 2. Okay, so the distance between planet 1 and the Sun, between the center of the Sun and the center of the planet 1 is R1. Okay, and the distance between the center of the Sun and planet 2 is this R2. Okay. The period, the time that it takes for planet 1 to go around and come back to the same position is period 1, and the time that it takes for planet 2 to go around and come back to the same point is period 2. Okay? Let me focus first on planet 1, and let me write Newton's second law for it. Okay, so the sum of the forces equals to ma. So for planet 1, what do we have? Well, this is the gravitational force, G, m1, planet 1, mass of the Sun, divided by the distance between planet 1 and the Sun squared. And this is going to be equal to the mass of the Sun, the mass of the planet, multiplied by a, centripetal acceleration, so it's v squared divided by r1. Okay? So this is similar to what we did for the satellite, right? So let me get rid of this m1, let me get rid of one of these r's, and so here we have this equation. Let's write this v squared in terms of r, the distance, and so this is going to be 4 pi squared. Now, so I'm using that, we are using again that expression that v is equal to 2 pi r divided by the period. So here I have 4 pi squared r1 squared and t1 squared. Okay, so let me put r and t on one side of my equation and all the constants on the other side. And you see that, what do we get? I will have r1 cubed, if I pass this to this side, divided by t1 squared, all right, which is equal to g m of the Sun divided by 4 pi squared. All right, and this is what you get here is just the opposite of what I wrote here, no? And so this is what you get. So let me put okay, so this equation is the same one, so let me write this one here for planet 1. So just by studying planet 1, we have that t squared, period squared, distance cubed is equal to a constant. If I do the same for planet 2, same list of equations, I'll get to the same stories, but I will just have to change, instead of period for planet 1, I have period for planet 2. Instead of distance for planet 1, I have distance for planet 2. But this is again just constant. And so this is constant, they are equal. And that's where that expression is going to come from. So this is equal to this. Okay? So this is where that ratio comes from. And then once you know this ratio, you can go on solving problems. The problems are easy. Now it's just plugging numbers into this equation. The only problem is that these are big numbers, so you have to be careful with your calculator and changing units.